We start with our lecture on atomic structure, periodic table and chemical bonds. In the last lecture, I had discussed about Aufbau principle and so what's Aufbau principle? It's about how the electrons are arranged in the atom, multi-electron atom in the quantum states. So it tells us that, it states that electrons are filled into atomic orbitals in increasing order of orbital energy level. So according to Aufbau principle, the available atomic orbitals with the lowest energy levels are occupied before those with higher energy levels. So this is applicable for the ground state. So ground state is the state of lowest energy of the atom. So what does it mean? So it means, so this is the diagonal rule. So this tells us about the Aufbau principle. So we are talking of multi-electron atom. So the atom can have more than, so we can have more, we can have more than, multi-electron means we can have more than one electron. We can have more than one electron. Now what we have is, so the first electron will go into this, what is called, okay, let me change the color, then it will be easier. So for the first electron, will go into the what is called the 1s orbital. So after that, the next electron, so once the 1s orbital has been occupied, then it will go, the next electrons will go into the 2s orbital. Okay, 1s, 2s. After that, the next electrons will fill the 2p orbitals. Then it will go to the 3s orbitals. Then the electrons will fill the 3p orbitals, and then we will have 4s orbitals. Next, then we will have 3d orbitals will be filled up, and after that 4p orbitals will be filled up, and then 5s. So you can see this is the direction, you can see the direction in which the orbitals are filled up. So we will now go to example to see what we mean by this Aufbau principle. So this, you can see the arrows, and before that we need to know two more rules, which is called the Hund's rule. Hund's rule tells us that every orbital in a sublevel is singly occupied before any orbital is doubly occupied. We'll come to that, what it means. And another thing we have to take into account when we are arranging electrons in an atom is the Pauli's exclusion principle. Pauli's exclusion principle. So no two electrons can occupy the same quantum state. So this is a very important statement, and this is also we will learn through example. So before we proceed further, we have to know there is a concept called the spin of an electron. Okay, spin of an electron. Like this is an atom. Okay, so this is an atom and this is an electron. So electron is say moving around the atom So this is one motion. So this electron can move around the atom in the space. This is the nucleus. So this is the nucleus, and this is the this is the nucleus, and this is the electron. So the electron will move around the nucleus. So this is one motion. Apart from that, you can consider for the time being that the electron also spins, like we have a ball. So this is a ball. So we have a ball. So just electron is like a ball, say, and the ball can spin, right? Like the earth spins, and we have day and night. Similarly, the electron, we can consider the electron to be spinning around some axis. So the electron can spin in a, say, in this counterclockwise direction. In this way, the electron can spin in a counterclockwise direction, an anti-clockwise direction, or the electron can spin in a clockwise direction. Okay, so if we measure the spin is like an angular momentum. Okay, so when we call spin, it's an angular momentum, spin angular momentum. So when we say spin, actually I mean spin angular momentum. Spin angular momentum. This is called the spin angular momentum. So when we are measuring the spin angular momentum in a particular direction, say z direction, then we can get only two values, and there is half h cross and another is minus half h cross. Okay, minus half h cross means if this is the z direction, say this is the z direction, so this is the z direction, so this is the z direction, then if we measure the spin angular momentum along z direction, then we can only get two values. One is plus half h cross, that means the electron, this will give us this, the electron is, this is called spin up. So we will, this is spin up. Okay, half h cross is spin up, and another one is spin down. So if you measure, it can be that the spin of the electron or spin angular momentum is along the negative z direction. So this is spin down. So this is spin down. So this is spin down. Okay, this is spin down. So spin up and spin down. These are the, so one is denoted by, so one is denoted by this up arrow, and another one is denoted by down arrow. So these are also quantum states of the electron: up state and down state, spin up state and spin down state. This is required when we arrange electrons in an atom. Now we go to the simplest. So hydrogen atom. Hydrogen atom has one electron. So let me change the color. So hydrogen atom has only one electron, right? Hydrogen atom has only one electron. And so how do we, like, so 1s1, we say the configuration is 1s1. 1s1 means we start with 1s. Okay, so we start with, so there is only one electron, so we will write it like this. We will just draw a box, and then this is one electron, either spin up or spin down. So this is 1s1 is denoted by this. This is my 1s. This is my 1s orbital. So in this 1s orbital, I put an electron, and that electron will be in the up state or the down state. So here I have drawn it as up state. Now next is helium atom. Okay, so for helium atom we have two electrons, and both the electrons will be in the 1s state. So this is again I am drawing the 1s. Okay, so this is 1s state. Okay, and so one electron will be like this and the other electron will be like this. Why? So this is the configuration. Why? Is this correct? If I say this is up and this is also up. This is 1s. Is this correct? No, this is not correct. This is not correct. Why? Because of Pauli's uncertainty principle. This is where we can see Pauli's uncertainty principle in action. Pauli's uncertainty principle. Pauli's uncertainty principle. So, where is the problem? Problem is somewhere here. So, if we write like this, so 1s is a quantum state, isn't it? So 1s is a quantum state, 1s is a quantum state, 1s is a quantum state, right? 1s is a quantum state. And in this quantum state, if we put two up electrons, okay, so in this quantum state, if we put two electrons whose spin state is the same, that means what we have done is two electrons. So this implies that two electrons are in the same quantum. Two electrons are in the same quantum state. It implies this, right? That both the electrons are in the same quantum state, and that is not allowed by exclusion principle. Pauli's exclusion principle, not uncertainty principle. Pauli's exclusion principle. This is not allowed by Pauli's exclusion principle. That is what we have learned. If you go back, no two electrons can occupy the same quantum state. This is Pauli's exclusion principle, and this is what is in action here. So this is wrong. This is correct. If we put one electron in the up state and one electron in the down state, then the two electrons are in different quantum state, and that is allowed. But here both the electrons are in the same quantum state, and that is not allowed by Pauli's exclusion principle. Okay, so this is the logic. So this is correct. So this is hydrogen atom and this is helium atom, and this is a stable configuration because helium is a inert gas. We'll come to that later when we study periodic table. Okay, next comes where the other ones. Okay, I missed this. 1, 2. Okay, so next we come to lithium. Lithium has number of electrons 3. Okay, so how will the electrons be arranged? So here it will be 1s2. 1s2 means we have this is the 1s orbital. So in 1s orbital we have one up state and one down state. This we know. And then 2s1, and next comes 2s1. So this is my 2s orbital. This will get filled up next. So there is only one electron, so you can put it in any direction, so we will put it in up direction. This is the configuration for lithium atom in the ground state. Next we have beryllium. So for beryllium we have 4 electrons. So the ground state configuration will be, it's easy to see, 1s2 2s2. That is, here we have 2 electrons. This is 1s orbital. So 1s orbital will be have one up and one down. Okay, 1s, and the other one is the 2s orbital. So this is the 2s orbital. So the 2s orbital, and that will be 2s. Okay, so 2s will be having 2 electrons. So the one will be up and one will be down. Okay, so Pauli's exclusion principle has to be respected. That is the thing. Just like this, we cannot put both up here or both down because of Pauli's exclusion principle. Pauli's exclusion principle. Pauli's exclusion principle. Pauli's exclusion principle. Next is, we have boron. So boron is 1s2, 2s2, 2p1. So we are following Aufbau principle here. As you can see, Aufbau principle we have already discussed. So this is, so first 1s, then 2s, then 2p. After that it will be 3p, 4s, like that. So for boron it is 1s2, 2s2. So this will be, so this will be, so this is the 1s, this is 2s, and then there will be 2p orbital. This is the 2p orbital. Okay, and you remember in 2p there are 3. So 2p orbital has, actually there are 3 orbitals. In 2p sublevel there are 3 orbitals. Is it not? In this 2p subshell there are 3 orbitals. This we can already, we have done this before. So let's go back. You can see here in 2p there are 3. Then 3s there will be 1. Again 3p there will be 3p sublevel, there will be 3 orbitals. Then we have 4s, then 3d we will be having 5. We will be having 5 3d orbitals. So 1s2 means one goes up and one electron goes down. 2s means again one is up, the 2 electrons. So you can see in only one, in this one box we can have only 2 electrons, one up and one down. Okay, in each such box we can have maximum 2 electrons, one up and one down. Here also we can have 2 electrons, one up and one down. So in this case we will have 2p1, so we can have only 1 electron here, and the other one, these and these will be empty. In any one you can put, so you just put this electron here, right? So now we'll go to the next one, carbon 6. So what is carbon 6? Carbon 6 has 6 electrons, and how are they placed? 1s2, 2s2, 2p2. So we have to just draw this diagram again, these boxes. So we draw the boxes. So one box, this is 1s, this one is 2s, and this one will be this one will be so this one will be, so now we can put this. So this is 1s, this is 2s, and this is 2p. So here it will be 1 up and 1 down. Just repeat what we have done here, 1 up and 1 down. We'll put 1 here, and next here there is 2p2, so there is one extra electron. So where does it go? So where does the extra electron go? Does it go here? So is it correct if I write like this? So if I say the next electron goes like this, this is wrong. Okay, this is wrong. Why? This is because of Hund's rule. Let's go to Hund's rule now. See, Hund's rule says every orbital in a sublevel is singly occupied before any orbital is doubly occupied. So it has to be singly occupied before it is doubly occupied. So this is not correct. The correct one is this one. So the next one will be, actually the correct one will be like this. Correct one will be like this. Correct one will be like this. So it will be, so this is one up electron, one down electron. So this is 1s, this one is 2s. So one will be up, other one will be down, and here we will have 3. In this 2p sublevel there are 3 orbitals. So 1, and this is incorrect. So other one will be go here. So all will be before any orbital is doubly occupied. That's what Hund's rule says. Sorry. Each orbital in a sublevel is singly occupied before any orbital is doubly occupied. So all the orbitals have to be singly occupied first before any orbital is doubly occupied. So this is the correct one, this is the wrong one. And what we have done is we have to take into account what is called here Hund's rule. Hunds, Hund's rule. So what we have respected here is Hund's rule, and that is how we have arranged the electrons in the atom. Got it? So the next one is nitrogen, and for nitrogen also is the same thing. So we draw first the 1s, then we draw 2s, and then we draw 2p. Okay, then we draw 2p, and then 1, 2. So this is 1s, and this is 2s, and this is 2p. So we just repeat what we have done before. Here, here, and then like this. So this is still this one, carbon 2p, and there is one more electron here in nitrogen. So where does it go? It goes here because of Hund's rule. So again here Hund's rule, we cannot put this electron here or here. So every orbital has to be singly occupied first before any orbital is doubly occupied. So again here Hund's rule is at play. Hund's rule is important. Okay, this gives you a stable energy with lowest. This gives the configuration with lowest energy. Then we go to oxygen. Oxygen is now very similar. So this is, we have to draw 1s, then we draw 2s, and then we draw 2p. So 2p means there will be 3 orbitals. So we put the electrons up, down, and then we have up, then we have up. So till this is nitrogen, and oxygen will have one more electron because it has 8 electrons. So where will this electron go? The 8th one, it will go in either here or here or here. So how will it go? Like this. Now we don't have, so again Hund's rule is here. So now every orbital is singly occupied. Now this orbital can be doubly occupied. So this is a correct configuration. So this is the electronic configuration of oxygen in its ground state. And then we go to electronic configuration of fluorine. Fluorine has 9 electrons, and this is just, we'll repeat what we have done before. This is the 1s orbital, this is the 2s orbital, and this is the 2p orbital. Okay, this is the 2p orbital. So this is up, down, we have done. We'll just repeat what we have done before for oxygen. So up, okay, and then we go to down here. This we have done before. So this down, and so fluorine will be, so this is 8, 4, 7, 8. Fluorine has 9, so next one will be in another orbital, and this with down. So this is the configuration for fluorine. Okay, and then what is it? So this is now what is the electronic configuration of neon. So electronic configuration of neon, again it's an inert gas. So neon is an inert gas. So this is just 1s and 2s and 2p. One, so this is 2 and this is 3. Okay. Again, we just have to repeat what we have done before. 1s, 2s, and then we have this, the 2p sublevel, which has 3 orbitals. So electrons are placed like this, and then they become doubly occupied, each orbital, and here we have 10. So this is neon, and this is again a stable configuration because neon is a inert gas, that is, it does not react chemically. So this has to be a very stable configuration. Stable configuration, very stable. this energy is very low. The energy of this configuration is very low, since it's stable configuration. So next is sodium. So now we know how to do it. So the sodium is Ne3s1, that is, we have to, this is the electronic configuration of neon. So this is the electronic configuration of neon, and then there is 3s1. Okay, so neon is already there. So this is neon we have done, this is neon. So whatever is, so neon, whatever the electronic configuration of neon we have done, and then 3s1. 3s1 means the 3s orbital. So this is the 3s orbital, and here we put one electron, say, in the up state. So this is the electronic configuration of sodium. And this is how we can arrange the electrons in an atom in its ground state. And so we will end today here, and in the next class we will see exceptions to Hund's rule, and exception to Hund's rule, and we will do a little bit of atomic structure before moving on to periodic table. So thank you.